Good morning everyone, welcome to today's GCSE Chemistry live group tutorial. Hope you all had a lovely evening and thank you for joining us this morning. So today's session is on Group 1 and Group 7 elements. You can see lots of you joining us who've joined us before. Welcome. Just a reminder that this session will run for 1 hour, so we'll finish at 11:45, and the way it will work will be our tutor Aman will run through all the content, and then at the end we'll have some time for some questions. So lots of you know Aman already. Aman studies medicine at King's College London and has completed over 150 lessons with my tutor. This should be a really good session today. As I said, this is GCSE Chemistry, Group 1 and Group 7 elements. So I see just a few people we're waiting on to join, so I'll just wait a moment. As usual, any questions you have for Aman or for myself until I work with my tutor, please pop those in the chat or the Q&A function throughout, and we'll do our best to answer those sort of throughout and at the end sort of in a bulk. So just let us know if you have any questions there. As usual, the session will be recorded and you'll be able to access it on the My Tutor YouTube channel, as well as all the previous recordings from all the sessions and some shorter videos related to the topics that all our tutors have been teaching over the past week. So those should hopefully be helpful for you guys as well. And if you want to join us for any further sessions today, we also have English, maths, physics and biology happening today. Cool, then in that case I think we'll kick off, if that's okay, Aman.
Yep, welcome back everyone. So as Tilly said, we'll be doing Group 1 and Group 7 elements today. And if we've got time, we'll have a look at the history of the periodic table. If not, we'll do that tomorrow with the transition elements. So just a quick recap of what we covered yesterday then when we started with the noble gases. So hopefully you'll remember that they have a complete outer shell of electrons. So if we look at our periodic table, the noble gases are group 0. So remember things like neon, argon, helium. And I drew the electron configuration of neon yesterday, so it has an atomic number of 10, and therefore it has 2 electrons in the first shell and 8 in the second shell, which means it has a complete outer shell of electrons, and that gives it its properties of being unreactive. So remember, reactions happen because electrons are either shared, gained, or lost. In the case of noble gases, they don't want to share or gain or lose any electrons because they've got a full outer shell of electrons. So that's why they are inert or non-reactive. And that means that they don't catch on fire, so they're non-flammable. It also means that they go around as single atoms, so they don't form bonds with each other or any other atoms. And that means that between atoms of the noble gases, there are only intermolecular forces there. So between neon atoms, you will find intermolecular forces. And that obviously gives the property of a low boiling point. So we covered that last week. So if there's intermolecular forces, there's little energy needed to overcome them, and therefore they have a low boiling point. But we discussed how they increase down the group because the atomic mass increases. And the final property was that the densities are low. So remember, density equals mass over volume. So in this case, the volume pretty much stays the same, but the mass of the atoms increases down the group. So as the relative atomic mass increases, so that means the density increases down the group. So that's just a brief recap of the noble gases. Before we move on to Group 1 or Group 7, does anyone have any questions about the noble gases? Otherwise, we'll move on. Okay, so there's no questions there, so we'll move on. So we're looking at the alkali metals today, or Group 1 first. So Group 1 is over here. So it's from lithium down to about rubidium. So usually in exam questions, they'd ask you from lithium to rubidium. They wouldn't ask you about the other two there. And we need to know some of their properties. So the main properties that we need to know about are that they are very reactive. And we need to know why that is. So before we go into that, because they're so reactive, we store them in oil. So because we store them in oil, it means that they don't react with oxygen in the air. So because they're reactive, they tend to react with oxygen in the air. So if we store them in oil, the oil protects the metals and stops them reacting. So that's why often at school, if you've done reactions with them, you'll find them stored in jars of oil. So their reactivity increases down the group. Now, this is quite a difficult concept to understand because there's 3 factors that are at play here as to why the reactivity increases down the group. So let's look at our periodic table and let's have a think about why that could be. So we've got lithium at the top, and potassium is the third one. So let's think about lithium and potassium. So if I draw the electron configuration of lithium, it has an atomic number of 3. So that means there are 2 electrons in the first shell and 1 electron in the in the second shell, which is what we're expecting because it's in group 1, so it should have 1 electron in its final shell, which in this case is the second shell. Potassium has 19 electrons. So if I draw that, it means in the first shell it will have 2. In the second shell it will have 8. That makes 10. In the third shell it will have 8. That makes 18. And then in its fourth and outer shell it will have 1 electron, again, which is what we're expecting because it's in group 1. So we want to know, why is potassium more reactive than lithium? So to understand this, let's think about the electron configurations. In reactions, I remember me saying that we either lose, gain, or share electrons, and we know that metals tend to lose electrons. So in lithium, it's going to lose this electron. In potassium, it's going to lose this electron to then form a positively charged ion. So why is potassium more reactive? Well, to lose this electron, it's got to overcome the force attracting that electron to the nucleus. So remember that in the nucleus we have neutrons and protons, and all these electrons are attracted to the protons in the nucleus, and that's because protons are positively charged. Exactly, someone's giving me an answer as to why lithium is less reactive, so really good. Well done everyone that's giving me answers. So as I said, the electrons are less attracted to the protons if they're further away. So in potassium, we can see that the outer electron is further from the nucleus. So there's a greater distance there, which means that there's less attraction of this 1 electron to the nucleus, which means that it can be lost more easily. Whereas in lithium, this 1 electron is quite attracted to the protons in the nucleus because there's less distance. So that means it's harder for it to be lost because there's more attraction there, so more pull into the nucleus. So that's the first reason. So it's about distance from the nucleus. The second reason is something called shielding. And shielding is about the electron shells between the nucleus and the outer electrons. So if we look at lithium, between the nucleus, which we'll imagine is here, and between the outer shell, there is 1 shell. That 1 shell shields the protons from the electrons. So effectively, it's blocking the electrostatic attractive force of the protons from the electrons. But there's only 1 shell in lithium, so there's not that much shielding. Whereas in potassium, there are 1, 2, 3 shells. And all 3 of these shells will try and block or shield the electrostatic attractive forces of the protons in the nucleus from the electrons. Someone's asking, can I write that down? Yep. So the first reason was about greater distance from the nucleus. So that means that there is less electrostatic attractive force between the protons and the outer electron. Remember, there's only 1 outer electron, so I've put outer electrons. That's the first reason for why potassium is more reactive than lithium. And then the second reason is about more shielding. So that is because there are more electron shells in potassium. And remember, they are between the nucleus and the outer shell, which shield the electrostatic attractive forces of the protons from the electrons. So remember, those protons are trying to pull the electrons in. Hold on, let me just make that more. There we go. So the electrons are trying to pull, the protons are trying to pull those electrons in, but because there's shielding going on in potassium, there's a lot more shielding than in lithium, there's less pull. So it's distance and shielding. Now there's one reason that counteracts these two. So these two are both saying that potassium is more reactive than lithium. Now the one reason that you might think that actually lithium is more reactive than potassium is because of the atomic number. So in lithium, the atomic number is 3. In potassium, the atomic number is 19. That means in lithium, there are 3 protons, whereas in potassium, there are 19. So you might think that in lithium, there are less protons in that nucleus, so there is less electrostatic attractive force between the protons and the outer electron. Whereas in potassium, there are 19 protons in the nucleus, so there's more positive charge in the nucleus between that outer electron and the nucleus. So that is actually saying that lithium should be more reactive than potassium. And the reason why that's not the case is because the 2 forces of greater distance and more shielding are more or greater than the atomic number being increased. So in an exam question, you would answer it with there being a greater distance and there being more shielding. But the one kind of criticism of this is that the atomic number increases in potassium, so therefore there's more protons, so you would expect there to be a greater electrostatic attractive force in potassium than in lithium, but that's not the case because these 2, the greater distance and the more shielding, are more effective, or they overpower the fact that there's more protons. Okay, so that's explained why the reactivity increases down the group, so greater distance from the nucleus and more shielding. They also have a very low density, which increases down the group. And this is exactly like the noble gases. It's because the mass increases more than the volume. So remember, density equals mass over volume, and the mass increases more than the volume. Someone's asking, what time does this session finish? It finishes at 10:45. The melting and boiling points decrease down the group, and they are soft. So if you've done experiments with these metals at school, you'll know that you can actually cut these metals, which isn't a usual property of metals. So you'll remember last week we covered the metals, and we said that most of them are hard because of their giant metallic structures, and that is the case. But the alkali metals are special in that they are soft, and the reason for that is to do with their metallic bonding, and it's also why their melting and boiling points decrease down the group. So remember I talked about this shielding and greater distance. So in our metallic structures, so remember they're positive ions you tend to form with a sea of delocalized electrons. And remember in our group 1 alkali metals, each atom will give 1 electron. So remember that's because there's 1 electron in the outer shell. There we go. So there's 8 electrons there and 8 positive ions. So what this means is that because the ions get bigger as we go down the group, the outer electron is further from the positive nucleus, which means that the electrostatic attraction between the electrons and the positive nucleus is less. So in the alkali metals, as we go down the group and the ions get bigger, less energy is needed to overcome the metallic structure, to overcome those electrostatic attractive forces. And that's why the melting and boiling points decrease down the group. Because as they get bigger, the protons are further from the delocalized electrons in that structure, so there's less electrostatic attractive forces, and therefore less energy is needed to overcome or break those electrostatic attractive forces between the delocalized electrons and the positive cations as we go further down the group. And the reason they're soft is because each positive ion only gives 1 electron, so there's not much electrostatic attractive force between that 1 electron and the nucleus, and that's why they are soft. And it actually happens that they become softer as you go down the group. So if you try and cut lithium, which is at the top, it's a little bit harder, whereas if you try and cut sodium or potassium, it's a lot easier, and that's purely because the melting and boiling points are decreasing, so it becomes easier to break it up. Someone's asking if I can write down the reason for the property of soft and melting and boiling point. Yes. So the melting and boiling points is because of the size. So melting and boiling points decrease down the group because the ions get larger, and therefore there is less electrostatic attractive force between the nucleus, and remember it's the protons in the nucleus and the and the delocalized electrons, and so less energy is needed to break them. So that's the reason for the melting and boiling points there. And then for the being soft, it's because of the fact that they have low melting and boiling points and only 1 delocalized electron cation, so weak electrostatic attractive forces. And remember, they get softer down the group. Okay. The other thing that I've got on this slide is about lithium being red, sodium being yellow, and potassium being lilac. That is not the colour of the solids, that's the colour of the flames produced. So you may have done this at school, where you put a piece of lithium in a Bunsen burner and the flame colour will go red. Someone's asking, why do the ions become larger? So the ions become larger because the atomic mass increases. So if I go back to the periodic table over here, I'm just going to move this out of the way. Remember here, lithium has an atomic number of 3 and atomic mass of 7. Sodium, an atomic mass of 23. Potassium, atomic mass of 39. So they're getting bigger and bigger. So those atoms and ions are getting bigger and bigger. Remember, they're ions because they're losing those electrons into the sea of delocalized electrons. Is this linked to chemical analysis? Sort of, yes. So the flame test that I'm talking about is chemical analysis. So you may be asked in exam questions, what's the, how do we tell if something is sodium? And you can talk about the flame test. They do react vigorously with water. We're going on to that in just a second. So this is my first slide on their properties. We're going to be talking about reactions in a minute. So we've talked about them being stored in oil because they are reactive, and we've said that they're reactive and they get more reactive as we go down the group because of a greater distance from the nucleus and more shielding. We've talked about them having a very low density because their mass increases, very low density because they tend to be quite small mass in a quite a large volume, but that increases down the group because the mass increases more than the volume. They are soft because there's weak electrostatic attractive forces between the outer electrons and the protons in the nucleus. And remember, those outer electrons are delocalized if we're talking about them as metals. The melting and boiling points decrease down the group. Again, that's because the delocalized electrons are less electrostatically attractive to the protons as the ions get bigger. And we've talked about the flame tests. So if we add lithium to a Bunsen burner, it's red. If we add sodium, it's yellow. And if we add potassium, it's lilac. Someone is asking, how would we tell if something has carbon dioxide or hydrogen? Excellent. So carbon dioxide classically turns lime water cloudy. That's the test for carbon dioxide. And hydrogen causes effervescence, which we're going to talk about. Someone's asking, what does D, M, and V stand for in the equation? D is density, M is mass, and V is volume. And why are they soft? They are soft because of what I've written here. Oh, and I've just noticed you can't see what I've written there. So low melting and boiling points and only one delocalized electron per cation. So there are weak electrostatic attractive forces between the protons in the nucleus and the delocalized electrons. Okay, so let's go on to their reactions. What would D, M, and V be in a triangle? Very good question. So some of you will know that we draw these triangles to help us when we're thinking about equations. So that's your triangle for density. So remember, if we want to know what density is equal to, we cover it up like that, and then we know it's mass divided by volume. So that's how the triangle works. Okay, let's go on to reactions. So there are 3 reactions we need to know about with the alkali metals. 2 of them are relatively simple. 1 of them is a little bit more hard to understand, and that's the one they tend to test a bit more as well. So first of all, you need to know how to balance all of these equations, and you would need to know how to write the written equations and the symbol equations as well. So if we start with the first one, they react with oxygen to form metal oxides, which produce white smokes. So on the slide, I've got an example. Lithium plus oxygen goes to lithium oxide, and it's balanced here. So remember, we talked about balancing equations on Tuesday, where we said the number of atoms is equal on both the reactant side, so on the left-hand side, and the product side. And that's because atoms are neither created or destroyed. That's the law of conservation of mass. So I'll do one more example here. This one to remember is a little bit simpler because it's just two reactants making one product. So for example, sodium be a solid. We know all the metals are solid, so that's solid. Oxygen we know goes around as a gas, so it's got an state symbol of a gas. Will then form sodium oxides. They form these metal oxides, and that will have a white smoke, and it produces a solid. Okay, so that's the first reaction. If you want the balanced symbol equation, remember sodium is just Na. Oxygen goes around in pairs, O2. and it's going to form sodium oxide. Now the hard thing, and I talked about this being a higher tier thing, is being able to know what does the chemical equation of sodium oxide look like, or the chemical formula. So we discussed this. We know that sodium as an ion will lose 1 electron, so become Na+, and that's because it's in group 1, it only has 1 electron to lose. Oxygen, if we go back to our periodic table, is in group 6, so that means it has 6 electrons in its outer shell. So that means it wants to gain 2 to get its full outer shell, and if it does that, it becomes an O2- ion. So then to do their chemical formula, if these two bonds, that means that one sodium has 1 electron to give, but oxygen needs 2. So we need 2 sodiums for every 1 oxygen. So that would be the formula there. So Na2O. And then if we're going to balance that, so remember, we look at what's different first. So if we have a look, our sodiums are not equal because we've got 1 on the reactant side, 2 on the product side, and our oxygens are not equal because we've got 2 on the reactant side and 1 on the product side. So first of all, we know we're going to have to make this 2 because we need our oxygens to balance. And now our sodiums have become 4, so that means we need 4. So that's the full balanced equation of sodium reacting with oxygen. And it's the same for all the alkali metals. So if you go back, so our alkali metals here are lithium, sodium, potassium. So you'd have to know how to do potassium plus oxygen as well. Okay, the next reaction is the harder one. It's the one where we react with water. So it's a classic one, and I'm actually going to show you a YouTube video, which will hopefully play. And this is reaction of potassium with water. So it's just taken some potassium out of oil, and we're going to see that it becomes very easy to cut. He's going to cut the metal now, and there you can see it's quite easy to cut. And you can see it's shiny inside. And that shininess is going to go away quite quickly because it's going to react with oxygen, as we've just done, so it's going to form a layer of potassium oxide. He's just testing that it conducts electricity, and we know that metals conduct electricity because of those delocalized electrons. And now it's going to add it to water, and there you can see the classic purple flame. And you can see there's effervescence going on, that's the hydrogen gas being produced, and then it dissolves. So we can watch it again, purple flame, it floats along that water. Remember, it's less dense than water, and then it's going to dissolve once it's finished reacting. Okay, so that, if you want to watch more videos of those, I would recommend it because it makes it easier to understand. So I've got on the screen lithium reacting with water. That was potassium in the video. So reactions with water, so lithium plus water will go to lithium hydroxide and hydrogen. So to understand these reactions, you will only ever be tested on lithium, sodium, and potassium, so the first 3 elements. Potassium's the only one that will produce a purple flame when it reacts with water, and that's just because it's so reactive, so it produces that purple flame. The other 2, lithium and sodium, will not produce a purple flame. They will react with the water. They will start off first by floating on the water, like you saw in the video, so it floats around on the water. You'll have effervescence because of the hydrogen. So someone asked me, how do we know if hydrogen's there? You'll get effervescence, and effervescence literally means bubbling. And as that lithium hydroxide floats along on the water, slowly the ball of metal formed, the lithium hydroxide formed, will get smaller and smaller until it dissolves. Someone is asking me, can you write down why they are soft? So I've already done that. And can you spell that? I'm not sure what you want me to spell. Someone's asked me what we're talking about. We're talking about group 1 elements and their reactions. Okay, so lithium plus water goes to lithium hydroxide and hydrogen. So if we did the same with sodium, so sodium plus water, we know sodium is a solid, we know water is a liquid, goes to sodium hydroxide. Again, to work out the formula for that, we need to know the ions. So sodium forms an Na+ ion, and hydroxide is OH-. That's something to remember. And therefore, when we react them, we only need one sodium with one hydroxide, so we form NaOH. Sodium hydroxide plus hydrogen. And remember, I said that these dissolve, so therefore they are aqueous, and hydrogen is a gas. So that's the equation, and we just need to balance that. So to balance it, we look at sodiums are balanced already, Na and Na. There's one oxygen, but it's our hydrogens at the moment that's the problem. We've got 3 on the product side and 2 on the reactant side. And remember, I said it's difficult to balance an odd number, so we need to make something doubled. So what we can do is we can double this. If we double that, we get 2 sodiums, and now we have 2 oxygens, 2 hydrogens plus 2 hydrogens here, so 4 hydrogens altogether, and we have 2 oxygens. So if we put a 2 here, we get our 4 hydrogens, we get our 2 oxygens that we need, and then we just need to balance the sodiums with a 2. And so now everything is balanced: 2 sodiums, 2 sodiums, 4 hydrogens, 2 hydrogens here plus 2 here, 4, 2 oxygens plus 2 oxygens. So that's the balanced equation of sodium reacting with water. And as I said, in exam questions, they tend to ask you what happens in the reaction. So I really do recommend watching YouTube videos of sodium, lithium, potassium all reacting with water. They're quite fun to watch, and they will help you to understand what's going on. Is sodium hydroxide alkaline as well? Yep, that's exactly what I'm about to go on to. So you may be wondering, why are the alkaline metals called alkali metals? And the reason is because of this hydroxide that's produced. So when it dissolves in solution, it is alkaline. So if we add a pH indicator to it with litmus paper, that litmus paper is going to form an alkaline colour, so purpley colour, and therefore it is an alkaline solution. So the reason they're called alkali metals is because when they react with water, they form an alkaline solution. Someone's asking, oh, effervescence. So effervescence is about hydrogen and it forming a gas. So remember that the hydrogen gas, the way to test for it is for bubbling and effervescence. So the final reaction we need to know about is the reaction with non-metals, so fluorine, bromine, and forming white solids. So if we react lithium with fluorine, so fluorine is a halogen, we're going to be going on to them in a second. Lithium reacts with fluorine to form lithium fluoride. I'll show you a different example. So if we do sodium, or actually let's do potassium with chlorine, we would form potassium chloride. So that one again is pretty straightforward. So the two straightforward reactions are the ones with oxygen and the ones with non-metals. The harder one to understand is this one here, where we react with water. So we're going to do some exam questions in a bit, and hopefully it will all make a bit more sense. Okay, so let's move on to the halogens. So halogens are the group 7 elements. So over here, it's fluorine, iodine down to astatine. In the exam, you can be asked about all 5. With reactions, you tend to be asked about chlorine, bromine, and iodine, but sometimes they ask about the properties of astatine and fluorine. So let's think about those properties then. What are they? So they have low melting and boiling points, which increase down the group. And that's exactly the same as the noble gases. It's because of covalent bonding. So remember that the halogens go around as pairs. And the reason for that is if we look at fluorine, first of all, fluorine has an atomic number of 9. So if I draw the electron shell of fluorine, there will be 2 electrons in the first shell and 7 in the second shell, which is what we're expecting because it's in group 7. So fluorine goes around in pairs because if it shares its electrons with another fluorine, so remember there'll be 2 here, and then 7, and remember there's going to be sharing going on. So let me draw that as a shared covalent bond. So remember we covered covalent bonds last week, so I drew it last week as almost like a Venn diagram, so like this. So if we just imagine the outer electrons, so we said there's 7 in fluorine, it will share 1, and then this one over here will also share 1. And then what we can see is that we have enough electrons to form our 8. So we've got 8 in this one and 8 in that one. So that's the covalent bond, and that's why fluorine goes around in pairs, because if it goes around in pairs, it forms its outer shell. But remember, when we're melting or boiling fluorine, it's not the covalent bonds that we break the intermolecular forces. So fluorine goes around in pairs, but we don't just find fluorine on its own as one pair. There's always lots of pairs in there, and there's intermolecular forces between each of the pairs. And it's these intermolecular forces that we break. And they are very weak, so therefore there's little energy needed to overcome them. But the reason that the low melting and boiling points increase down the group is because you'll remember that intermolecular forces increase if the atomic mass increases or if the atoms get bigger. And we know that as we go down the group of halogens, we can see that the atomic mass gets bigger. So astatine has an atomic mass of 210, it's got 85 electrons, whereas fluorine only has 9. So they're getting bigger. And as they get bigger, the intermolecular forces increase. So that's why the boiling points and melting points increase down the group. Hopefully you remember from last week that covalent bonding means that there's no electrons free, and so therefore covalently bonded structures do not conduct heat and electricity. The only difference is graphite, which will conduct electricity because it's got delocalized electrons within its layers, but every other simple molecule does not conduct heat and electricity. Now, the one thing that we need to cover then is why do they become less reactive down the group? So we said that the alkali metals become more reactive down the group, but the halogens become less reactive down the group. And it's exactly the same reasons as the alkali metals. It's to do with distance, shielding, and the atomic number. Excellent, people that are giving me answers, you are exactly correct, well done. So if we talk about distance first, so I'm going to draw the electron structures of fluorine and chlorine. So it's 9 and 17 for the atomic number. So I've already drawn fluorine, so we know that there's 9 electrons, so there are 7 in its outer shell, again, which is what we're expecting, and chlorine has an atomic number of 17. So there'll be 2 in the first shell, 8 in the second shell. 2 plus 8 is 10, so that means there are 7 in its third shell, again, what we're expecting because it's in group 7. Okay, so why is it easier then for fluorine to gain an electron than for chlorine? Because remember, reactions are all about losing, gaining, or sharing electrons. We know that halogens are non-metals, so therefore they like to gain electrons. So why is it easier for fluorine? Because we said that they become less reactive down the group. So that means it's easier for fluorine to gain an electron than chlorine. So for fluorine to gain an electron, that electron needs to be attracted to the protons in the nucleus. So what that means is if this one here wants to gain that electron, it's easier for fluorine because this outer electron, or the outer electron shell, is closer to the protons in the nucleus. So there's more electrostatic attractive force between the protons and the electron that needs to be gained. Whereas in chlorine, if we want to gain that electron here, there's less electrostatic attractive force because it's further from the nucleus. So it's harder for this electron to be gained because remember, if we want to gain an electron, there needs to be some pull from the positively charged protons in order to gain that electron. So that means that fluorine is more reactive than chlorine because it's easier for it to gain that electron due to the distance. So that's the first reason. Excellent for people saying that it's closer to the nucleus. Shielding here is also taking an effect. So in fluorine, there's only one shell. There's only one shell of shielding going on. So that means that there's less shielding in fluorine compared to chlorine, where there are 2 shells between the outer shell and the nucleus. So there's more blocking of the proton's electrostatic attractive force in chlorine than there is in fluorine. So in fluorine, there's only one shell shielding, whereas in chlorine, there's 2 shells shielding. So if that electron wants to be gained, it's harder in chlorine because we've got 2 shells shielding that positive force from the protons from the electrons. So the positive force of the protons wants to pull that electron in, but we've got these 2 shells shielding that positive force, almost like blocking that positive force. So it's harder to gain 1 electron here than in fluorine when there's only 1 shell. So they're the 2 reasons for why the halogens become less reactive down the group. So well done to anyone that was telling me those answers. You were exactly correct. Okay. The only reaction we need to know about with halogens, and the one that is often tested, is about a more reactive halogen displacing a less reactive halogen. So displacement means that it effectively removes it. So if we look at chlorine reacting with sodium iodide, if we go to our periodic table, I said that the more reactive halogens are the ones on the top because they get less reactive down. So this is chlorine reacting with sodium iodide. So chlorine is more reactive than iodine because it's higher up. So that means that if we react chlorine with sodium iodide, what happens is that the chlorine will displace the iodine to form NaCl plus iodine left on its own. So I've not balanced that equation yet, but that's just to show you what happens. So when we react chlorine with sodium iodide, the iodine gets displaced. That means it gets removed from the equation and chlorine takes its place. So it becomes sodium chloride and we're left with iodine. And the only thing we need to know is what color that forms. So often when we do this reaction, we form colors, and the color depends on which halogen is left on its own. So in this case, iodine is left on its own. So iodine in solution will tend to form a brown or a red-brown color. If this reaction was between chlorine and sodium bromide, so remember bromine is less reactive because it's chlorine is above it. So if it was between chlorine and sodium bromide, that means we'd be left with bromine. So I'll write that equation out. So chlorine plus sodium bromide, we'd be left with bromine on its own. So this bromine here will form the color of the solution, and bromine tends to be orange in solution. And the only colors you need to know are iodine, bromine, and chlorine. And chlorine, so if we reacted fluorine with sodium chloride, we tend to form sodium fluoride because the fluorine will displace the chlorine. Fluorine is more reactive. Someone's asking me, how did I do that? I'm not sure what you mean, how did I do what? And then we'll be left with chlorine. Chlorine forms a greenish, so it's like a pale yellow green solution. So we do need to know those colors, those three colors there, and it's always dependent on what's left. How did I know bromine would be alone? So the reason I know bromine will be alone is because of displacement. So when we react chlorine with sodium bromide, if we look at our periodic table, chlorine is above bromine. So remember I said they get less reactive down the periodic table or down the group. So that means chlorine is more reactive than bromine. So when we react chlorine with sodium bromide, because chlorine is more reactive, it will remove the bromine from the formula and form sodium chloride, leaving bromine on its own. And it's the same when you react chlorine with sodium iodide. Again, chlorine is more reactive than sodium iodide. So the iodine will be almost kicked out of that formula, leaving sodium chloride and iodine on its own. The same when we react fluorine with chlorine. Remember, fluorine is more reactive than chlorine. So when I did fluorine plus sodium chloride, the chlorine is kicked out. So you get sodium fluoride left with chlorine. Okay. So this is not the same as what I've just been talking about. This is what they look like at room temperature. So fluorine and chlorine are gases at room temperature. And remember I said that the boiling point increases down, the melting and boiling points increase down the group. So fluorine and chlorine have a very low boiling point, and that's why they are gases. But as the boiling and melting points increase down the group, the states change. So bromine is a liquid. So that means it has a very high boiling point, so it's not turned into a gas yet at room temperature. Iodine is a solid, so that means it has a very high melting point, so it's a solid at room temperature, and astatine is also a solid. This is what they look like at room temperature. So if you found fluorine gas, it would be yellow, chlorine gas green, bromine a red-brown liquid, iodine a dark grey solid, and astatine a black solid. In solution, they are different. So remember I said bromine forms an orange solution, iodine forms a red-brown solution, and chlorine forms a pale yellow solution. You need to know about what they look like at room temperature, what state they're in, and also what colours they are in solution. Someone's asking me to go back to the properties slide, so I've gone back to the properties slide. There we go. And these are the equations that I've written as well. Okay, so I think we'll do some exam questions now. We've covered quite a lot today, and I do appreciate this is quite a difficult topic. So if you're feeling overwhelmed, don't worry. What I would recommend is doing lots of exam questions. Someone's asking me, can you explain why the group 1 elements have low density? Yep, so group 1 elements, pretty much as we go down the group, the mass increases more than the volume. So remember that density equals mass over volume. If the mass in one element, so is, let's say in lithium, is 3, whereas in potassium or something, it's 19, the mass increases more than the volume. So if the volume stays at 10, what we can see is that the density increases. So the density in lithium would be 3 and the density in potassium would be 19. So it's about the mass increasing more than the volume, and that's why the densities increase down the group. But they're low because they tend to have quite a low mass in quite a big volume. Can you explain how to balance equations? I don't have time for that today. If you want to know how to balance equations, if you go back to Tuesday's tutorial, I did balancing equations there. Yes, I'll go back to the slides on the different colours. So as I said, the colours in this table are the colours that they are at room temperature, but these are the colours that they form in solution. Okay, let's do some exam questions because I'm conscious of time. If we have some questions that come up during that, then we'll go through that. So someone's asking me why group 7 have lower melting points. Remember, it's about the intermolecular forces increasing with the size of the atoms. So as we go from fluorine to astatine, the relative atomic masses increase. So that means that the intermolecular forces increase. So intermolecular forces get bigger with the size of the atoms. And if the intermolecular forces are stronger, that means more energy is needed. You wouldn't need to know what fluorine forms in solution because nothing will displace fluorine. Remember, it's the first halogen. So that's why I've said these are the only 3 colours you need to know. Okay, so we're not going through that now. Okay, all right, here we go then. Describe and explain the trend in reactivity of the alkali metals. So what's the trend in reactivity of the alkali metals and why are they? So remember, there's 2 reasons. So you get 4 marks, 1 for explaining the trend and 3 marks for explaining the reasons well. So does anyone know then, what's the trend in reactivity first? The group 1 elements, do they get more reactive as we go down or do they get less reactive as we go down that group? Brilliant, so they get more reactive as we go down. Okay, so we've got 1 mark for saying that. Someone said less. Remember, that's halogens that get less reactive as you go down the group. The group 1 elements get more reactive as you go down the group. Well done, everyone. Why do they get more reactive? There's 2 reasons. So why do they get more reactive? Distance and shielding. Excellent. So just to explain those again, the first one is distance, and that is as we go down the group, the outer electron becomes further away from the positively charged nucleus. Remember, there are protons in that nucleus. They are positively charged. So as they get further away, there's less electrostatic attraction between the protons in the nucleus and the outer shell electrons. And what that means is it's easier for an electron to be lost because there's less pull to the nucleus. If there's less pull to the nucleus, it can be lost. The second reason is shielding, as everyone's saying, and shielding is because as we go down the group, there are more electron shells between the nucleus and the outer shell. So if we go back to this, how did I do it here? Okay, if we have a look here, potassium is more reactive than lithium, and it's because if we look in potassium, there are 3 shells between the nucleus and the outer shell, whereas in lithium, there's only 1 shell between the nucleus and the outer shell. So there's more shielding in potassium. And what that means is that because there's more shielding there is less electrostatic attractive force between the outer shell electrons and the protons, so that outer electron is more easily lost in potassium than in lithium. So as you go down the group, they become more reactive, and it's because of there being a greater distance and more shielding. So effectively, the electrostatic attraction between the protons and the electrons is less. Okay, well done, everyone. All right, lithium is in group 1. It reacts with water to produce a gas and an alkaline solution. So does anyone remember which gas is produced when we react a group 1 element with water? Excellent, very well done. It's hydrogen. Which ion causes the solution to be alkaline? So does anyone know, we didn't cover this, but does anyone know which ion causes the solution to be alkaline? Excellent. It's hydroxide. Well done. Very well done. Hydroxide is alkaline. Okay. Potassium is also in group 1 of the periodic table. Potassium reacts with water in a similar way to lithium. Write down 2 differences you would see between the reactions of potassium and lithium with water. So what do we think? So we saw the reaction of potassium, and I definitely explained one difference. Does anyone know what those differences are? So between potassium and lithium reacting. Good, excellent. Okay, so we get the color of the flame. So potassium will have a lilac flame. There's no flame with lithium, excellent. And potassium is more reactive, excellent. So that's the 2 reasons. So you get this lilac flame with potassium, and potassium is more reactive than lithium. So it will happen faster, and that's why you tend to get that flame, because it is more reactive. So well done, everyone. Okay, when sodium is added to cold water, it forms a molten ball which floats on the surface of the water. Why does it float on the surface of that water? This is a slightly more tricky question. Does lithium have a crimson red flame? Yes, it does have a lithium red flame, but it won't produce that red flame when it reacts with water. It only produces that red flame if we add it to a Bunsen burner. Excellent. Everyone's saying it's less dense than water. Brilliant. That's why it floats on water. Really well done. Good. So when it reacts with that water, it is less dense. Okay, should we try and write the balanced equation for the reaction of sodium with water, and then we'll go on to the Q&A. And if there are no Q&A questions, we'll carry on with exam questions. So the balanced equation for the reaction of sodium with water. Does anyone have any ideas? Someone's saying, I don't understand this question. Okay. So the question was, when sodium is added to cold water, it forms a molten ball which floats on the surface of the water. So if you were here when we were watching that video, you'd remember in that video, they added potassium to the water, and we got a little ball of potassium hydroxide forming, which floats on the water before it then dissolves. And the reason it floats on the water is because it's less dense than water. So that means it floats. Okay, what's the balanced equation for sodium and water then? All right, well done. So sodium reacts with water to form sodium hydroxide and hydrogen. Well done, everyone that's giving me those answers. So sodium plus water will go to sodium hydroxide plus hydrogen. And if we're going to balance it, how do we balance that? Excellent. So if we have a look, our oxygens are already balanced, but our hydrogens are the ones that aren't. So remember I said we don't like odd numbers, and there are 3 hydrogens on the product side at the moment, but there are only 2. So to make that even, we put a 2 here to make it 4 hydrogens. That means we need to put a 2 here to give us 4 hydrogens. Now we have 2 oxygens, and we have 2 oxygens. The only thing unbalanced is the sodium. So the full balanced equation is there. Excellent, well done everyone that gave me that. You were exactly correct. Okay, someone's asking me what grade would group 1 and group 7 questions be in GCSE. So for the foundation tier, you would need to know the reactions themselves and the properties. You wouldn't necessarily need to be able to explain them, but you might be asked which one is more reactive or something like that. The higher tier, you need to be able to do balanced equations. You need to be able to write those equations. So for example, here we had to know it was sodium hydroxide and hydrogen that were formed, and you need to know how to form those equations. If it doesn't specify whether or not it's a word equation, do we assume it requires the symbol equation? So in this question, they said balanced. If they say balanced, that always means chemical equation, because you can't balance a written equation. So balance, they will very rarely say write an equation. They will either say balanced or word equation. If they say balanced, it means use symbols. If they say words, use words. Okay, let's go on to the Q&A, and then if there aren't many questions, we'll do some more exam questions.
Yeah, it looks like not many questions throughout. If you guys have any questions, then just pop them in now. Just have a look back.
Someone's asking me, do we need to add the state symbols? You only need to add them if they ask for them. I would avoid doing it unless you're certain of what they are, because you can actually lose marks. So if, for example, you accidentally put sodium hydroxide as a solid rather than aqueous, you could lose that mark. So I wouldn't put them in unless you're sure of what they are, or unless the question asks for it. So this question hasn't asked for it, so you don't need it.
Great, and what does molten mean?
Molten means that it forms almost like a liquid substance. So if you imagine like a volcano, the solid that pours out of a volcano it's called molten. It's almost like a liquid solid. So it's between the state of solid and liquid. So when the hydroxide forms, it's almost between the state of solid and liquid, and then eventually it dissolves in that liquid. So it's kind of that state change. It's a thick liquid almost.
Great. And how do we know what element or compound is what state?
Very good question. So at GCSE, they very rarely ask you to do it, but there are some that you should know. So for example, all of the metals bar Mercury are solids at room temperature. So we know that, for example, sodium is a metal, so it would have a solid state. You know that water at room temperature is a liquid. In the reactions that we went through with the alkali metals, I talked about sodium hydroxide being dissolved in water. And remember, if something dissolves in water, it's aqueous. So that's why sodium hydroxide is aqueous. And again, hydrogen is a gas. We know that. So it goes around as a gas. They wouldn't expect you to write the state symbols unless you've covered it. So the reactions we covered today, I put in all the state symbols. So those ones you should know. And hopefully they make sense, but ones that, for example, you haven't covered, you wouldn't be expected to know.
Thank you. Could you quickly go back to the colours and state table?
Yes.
I think a couple of people just wanted to have a look. And someone's asked, why are group 1 elements soft?
So group 1 elements are soft because of the weak metallic bonding. So remember, in giant metallic structures, you've got the cations. So you've got cations, and they're cations, so they're positive ions. And you've got your delocalized electrons. In group 1 elements, remember, each cation gives one delocalized electron because there's only one electron in its outer shell. So there is actually weak electrostatic attractive force between that one electron and the positive ion. And the reason the melting and boiling points decrease down the group is because as the ions get bigger, so remember down the group, the atomic mass increases, the electrons, those delocalized electrons, are less electrostatically attracted to the positive ions because the positive ions come from the protons. And if those protons are in the nucleus, as the atoms get bigger, those protons are further away from those delocalized electrons. So that metallic bonding is quite weak. And that's why these metals tend to be soft, and they also have low melting and boiling points.
Great. And would mercury and hydrogen be soft as a solid?
So mercury is a liquid at room temperature. You can make it a solid. It would not be soft because it's a transition metal, which we're going to cover tomorrow. Hydrogen, you can't really make a solid. That's pretty much a gas. Again, it's difficult to say whether it would be soft. So we don't tend to talk about covalently bonded molecules as soft. So it's not the right word to use.
Great. And what is a noble gas?
A noble gas is what we covered yesterday. So if I go here, noble gas is group 8 or group 0, so over here. They have a full outer shell of electrons. That's why they're often called noble. They can't give off any electrons or share any electrons because they've got their full outer shell. So noble gases are from helium down to radon. And if you want to know more about them, we covered them in detail yesterday.
Thanks. And does ionic bonding happen with 2 metals?
No. So if you go back to 2 weeks ago on Friday, we covered ionic bonding. It's between a metal and a non-metal. So there's 3 types of bonding. Ionic bonding occurs between a metal and a non-metal, and this red zigzag line on the screen is the difference between metals and non-metals. So metals are on the left-hand side and non-metals are on the right-hand side. Covalent bonding occurs between 2 non-metals. So remember, we were talking about fluorine going around in pairs. That's because it's covalently bonded. So 2 fluorine atoms are covalently bonded. And metallic bonding occurs between metals. So usually metallic bonding is with, say, lithium reacting with lots of different lithiums. So when I drew the metallic structure over here, this is all different atoms of lithium now forming ions. So that's the 3 types of bonding we need to know about.
Great. And do you know what would the hardest balancing equations question be?
The hardest, okay, that's a very difficult question to answer. I don't know off the top of my head what the hardest balancing equation would be. What I would say is that often we can get confused if something is odd and something is even. So remember when we were balancing, let me go to here. Okay, when we were balancing sodium hydroxide, which, there we go. So if you ignore us balancing it, the hydrogens on the product side, so on the right hand side, are uneven. So we've got one hydrogen here and two hydrogens here, so that means 3. If you ever see an odd number and to balance it you would need a fraction, so for example over here we've got 2 hydrogens on the reactant side. If we wanted to balance that, we would have to put 1.5 there to make 3, and to make 3 on the product side. So if you ever see that, make it even. That's my best tip for you. Always make it even. It just makes it so much easier. So start with something that's odd, and if it is odd, make it even. So in this case, if we add a 2 here, that's not going to make it even. That's still going to keep it at 5. So because there'd be 4 there plus 1 hydrogen makes 5. If we put a 2 here, it makes it even. So if you make it even, it's a lot easier to do. I've not seen many difficult balancing equations now, purely because if they ask you to balance an equation, it usually has to be related to the question that they're asking. And for it to be a full question, it has to be something you've covered. So I wouldn't be too worried about balancing equations. Just keep practicing lots of examples and you'll be fine.
Great. So maybe for the last few minutes, should we run through another question?
Yep, that's absolutely fine. Let's do that. 1 second. Okay. Okay, the elements chlorine, bromine and iodine are part of group 7 in the periodic table. The appearances of chlorine, bromine and iodine at room temperature are shown below. Predict the appearance of astatine. So we can either predict, or some of you may know because we did cover it today. So what do they look like? What does astatine look like? Good. Okay, so people that are saying black, you wouldn't get the mark for just saying black. You need to say black solid. So if we have a look here, we can see that iodine is a grey solid, so it's probably going to go black, and it's also going to be a solid. So well done for people that said black solid. The order of reactivity of chlorine, bromine and iodine can be determined by carrying out displacement reactions. Explain how displacement reactions can be used to show the reactivity of these elements. So this is a 6-mark question. It's a long question, so that means we need a lot of detail and we need to be quite clear. So does anyone have any idea? The order of reactivity of chlorine, bromine and iodine can be determined by carrying out displacement reactions. Explain how displacement reactions can be used to show the reactivity of these 3 elements. Any ideas? Someone's talking about shielding. Okay, further up is more reactive and it displaces. Good. Someone's asking me what are displacement reactions. So remember, displacement reactions are, for example, if we reacted chlorine with potassium iodide, the iodine is less reactive than chlorine, and that's because in the periodic table, remember it goes fluorine, chlorine, bromine, iodine, astatine. So what that means is that fluorine is more reactive than chlorine, chlorine is more reactive than bromine, and so on, because the reactivity decreases as we go down the group. So if we react chlorine with potassium iodide, because the chlorine is more reactive, it removes the iodine from the solution and produces potassium chloride plus iodine. And remember I said, what colour will that form then? Does anyone remember what colour if we've got iodine left? Brown. Excellent. Well done, people saying red, brown or brown. So the way to answer this question would be to talk about the equations that you would need. So we need to show that chlorine, bromine and iodine can be determined by carrying out displacement reactions. So you could talk about the trend. So you can say that the halogens become less reactive as we go down the group. Therefore, if we react a more reactive halogen with a less reactive one, it will displace it. And then you can either write the equations of 2 or 3 of them to show this, or you can write it out as words. So the way to answer it is to talk about chlorine displacing iodine, therefore chlorine is more reactive than iodine. And then you need to do bromine and iodine to show bromine is more reactive than iodine. And you need to do chlorine and bromine to show chlorine is more reactive than bromine. So you need to do 3 equations there to show that chlorine is more reactive than bromine and bromine is more reactive than iodine. Okay, well done for everyone that answered that. Excellent. So I think that's the end of our exam questions for today. As I said, tomorrow we'll be covering the transition metals, and if we've got time, we'll look at the history of the periodic table, because I know someone asked me yesterday if we can cover that.
Brilliant, thanks Aman, and thanks everyone for attending today. Lots of good questions and lots of good answers as well. So if you want to join us for any other tutorials today, we've got English coming up at 11, we've got maths at 12:15, physics at 2, and then biology at 3:15. If not, then hopefully see you in another chemistry session soon. And thank you very much, Aman, for a great session. See you guys soon. Bye.
Bye.